Yes. So welcome everyone. Welcome back, and also welcome newcomers. Today is the 6th session of the quantum computing class on Hackaday. And I'm recording this. The past videos you can find in the Hackaday project. The link here shows the comics and recording and the slides. Every Wednesday and Sunday, I post some new comics for the week on my social media and the Hackaday project. So if you miss anything, you can always go back. So just for newcomers who are not familiar with the format, we spend 30 minutes on Sunday, like right now, discussing one concept. We previously have covered quite a lot of basic concepts and software. How do you program and how to write the Q# language to use quantum computers. So today is very exciting. I know a lot of people asked me to talk a bit about hardware, and we're gonna do an overview of all kinds of hardware. So in terms of hardware, I wouldn't claim that I'm an expert in any of the types of hardware that I'm gonna show today, because I don't anymore work on the hardware hands-on directly. I used to work on similar systems, but they were not for quantum computing. So it's called low temperature physics and condensed matter physics. So if anyone in the audience works on any specific hardware system in the lab, I would love to have you on this and share your knowledge in particular hardware system. So no one can really claim that they know everything about all kinds of quantum hardware. No one, but then they can be very specialized in certain types. So if any of you work on this as your day job, please let me know. So today we're gonna give a brief overview to give you an idea of the different types of things we can try. In terms of making computing hardware, we already are using our electronics every day, computers and phones. They're based on transistors. From probably the first session, I've already mentioned that transistors are like very tiny switches. You can make them out of semiconductors and layers of semiconductor insulators and metals. You can form in the material areas where you can control the doping, the electronic concentration in different areas. By applying certain gates, you can allow electrical current to go through from source to drain, or you can stop it. So this can give you a on and off. So that's how in the transistors we make 0 and 1s. For qubits, we already know that we are only dealing with 0 and 1, and we need to make them into superposition. So all you need is some system that provides 2 types of states, and you can put them in superposition. Naturally, we want to use something that already exists, that already gives us 2 levels that we can use as 0 and 1s. One of the candidates is electrons. That's the simplest, the purest we naturally exist, we could look at using. But then think about how small electrons are, and they are everywhere. How do we isolate them and control the electrons to do what we want? We need to form certain structure to contain electrons. But before I go there, I want to just briefly mention this concept about electron spin. This is discovered a long time ago when quantum mechanics just became a new field of study. The Stern and Gerlich, they built an experiment to shoot a beam of electrons through a magnetic field. Back then, they didn't know about the concept of spin. and they were just trying to see what they would observe when the electron beam goes through the magnetic field. Without knowing the existence of spin, they would think, oh, electron is negatively charged, and then through a magnetic field, it would deflect into one direction. To their surprise, they observed two beams merging out of the electrical field. And there must be some physical parameter that they were not accounting for. And turned out it was the spin. That's how spin was discovered. So electrons and all kinds of fundamental particles have spin. Electron has one of the simplest is just spin up or spin down. And this is just, I don't want to confuse people who haven't ever seen this before, but for physicists in the room, they use this spatial representation to show the parameter of spin. So we could use this spin up and down as the 0 and 1s. So how do we confine electrons into controllable format? There's a lot of engineering, we can artificially create materials to confine electrons the way we want. So we can actually constrain electrons into different dimensions. In bulk materials, that's what naturally exists. In 3D, electrons are just inside the materials, and they can conduct electricity, they can flow around. But in some materials, we can make them into 2D. So electrons will be confined into only this lateral direction. We can even further confine them into 1D. That's like in the nano wire. And then we can further trap them into 0D. So this is like artificially trapped, and this is what we can create like a quantum dot. So how do we create a quantum dot in order to trap electrons into 0D, and in that case also to isolate electrons so that we can manipulate them? This is typical structure using alumina, gallium arsenide, and gallium arsenide, two similar semiconductors, but they differ by this dopant alloy here. At the interface, they can form this two-dimensional sheet of electron. So for people who have learned solid-state physics, this is the 2D electron gas, 2DEG. You can further apply metal gates on top of the materials and apply electrical current voltage. This potential here would remove some of the electrons underneath the gate. This is called a depletion region, where electrons are depleted from the 2D electron gas. Then what's left with is this region that you can gradually remove more and more electrons until you just have one electron kept in this little region here. This is called a quantum dot. So that's, in a way, reducing the dimensionality of how electrons can sit in the material, and then create this 0D structure where you can trap a electron here, and you can measure its spin, and you can apply voltage or electromagnetic field to change its spin. Then in this way, you can create a row of electrons, you can create multiple of them, and then control each of them to build this correlation and entanglement between them. But this is very, very difficult. You have to really be able to manipulate electrons at the individual level. So a lot of research has been done. That's one way of doing that, but a lot of current work on the quantum dot electron for qubit applications is still being done in research. And there are other ways to trap electrons, such as using the crystal lattice. Instead of in semiconductors and building the reducing dimensionalities one by one, we can also use naturally formed crystals like diamonds, or maybe not naturally, we can also grow diamonds in the labs. And you can carefully remove 2 carbons inside this lattice, have a vacancy and a nitrogen replacing one of the carbon. Because nitrogen has 1 more electron than carbon has, you can have this electron trapped here in this nitrogen vacancy region. And you can then apply light microwave to manipulate the electron there. That's using electrons, and you can think that it's pretty difficult to do that controllably. Like in the diamond vacancy is essentially using the defects inside your material. And sometimes it's very hard to even control where your defect will form. You have to grow your diamond very carefully. So scalability is very difficult. But there is not limited to use electron. There are other particles we could use, such as ions. Ions are ionized atoms. So atoms are neutral, but ions, you can form them by removing an electron, adding an electron, and having this charge on the ions. And it itself would carry a spin as well. You could think about it as a spin for iron that you're using, but in fact it's more complex. So when you have iron, you would be able to measure the electron levels inside the iron. But because of the existence of spin, your energy levels could split. This is called a fine structure. If you're not familiar with the term, don't worry about it. It's just when there's spin of the electrons in the iron energy level, it would split further into more levels. And then there's also another splitting called hyperfine structure, is caused by the interaction between electrons and their nucleus. And don't worry if this is not the most familiar concept for you, but just take it that inside irons, you will have a energy structure where electrons of the irons could sit onto. And you could use 2 of the levels inside the irons to be your 0 and 1 states. It could be from the fine structure, or it could be from the hyperfine structure, as long as you know what you're doing and you know which levels you're controlling. So people have built all kinds of ion traps. These are electrodes where you can form an electromagnetic field, and you can trap the ions into a row. Then you can apply laser beams to manipulate each individual ions trapped inside. And in the cartoon view, they each have their own spin, and you can change the ion's spin by using a focused laser beam. So that's how you can use ions to use their spins as the qubit. And that's based on the 2 of the levels from their electronic structure. So trapped ions have also quite a long history. It's built in the labs. It had a very complex optical setup. You have to have vacuum tubes to trap the ions and use a lot of laser beams to manipulate them. So for a while, it was thought that it's very difficult to scale, see how complex this setup is. and you have to have a lot of lasers. But recently, just in the past couple years, there were a lot of effort and in the industry that really started to scale these things down in terms of complexity and size. Now you can build chip structures that have ion traps or built on chip. This is a picture from Honeywell's on-chip ion trap, which is really cool. And they are actually a partner with Microsoft that we could use Q-Sharp to program the ions on these chips. So that's for the ion traps. Since electrons and ions are both using energy levels, we could also try to make artificial atoms. Electrons and ions are natural particles, but we could also mimic it in a circuit. So we could build a oscillating circuit using a superconducting component called Josephson junction and a capacitor, and then form this circuit on chip. Because the Josephson junction is a special type of inductor, so if you are familiar with LC circuits, what does it do? It basically forms a oscillating energy signal. Yeah, just a quick some quick pictures to show you there all kinds of architecture that you can build on chip, making those LC circuits. And so if you're familiar with the LC circuit, you would know that its energy versus frequency would be like a harmonic oscillator shape. When you reduce it to a really low temperature and make it very, very small, it then enters the quantum regime. When this circuit becomes a quantum circuit, it would just split into discrete energy levels. So you could use those levels as your zeros and ones, but then in the case of a LC circuit, a normal inductor, all these splitting would be the same width, which means when you apply a certain energy to your system, you wouldn't be able to control if your system is exchanging between these two levels or exchanging between these two levels. So a normal LC circuit is not that useful. Then what people did was to replace this inductor with the Josephson junction. And what it does is it modifies its oscillating profile to be uneven. So you still, when it's in the quantum regime, you get these splitted discrete energy levels. But then the spacing is different between each two levels. Then you can control which two levels you want to use. So you can pick the ground state as your 0 and then the excited state as your 1. And you can apply an electromagnetic field to exchange between these two. So this is the basic working principle of the superconducting circuit and how to use it as a qubit system. And I want to point to this here that showed a swing, and is saying that if we were small and cold enough, then we could be qubits. And what does that mean? Because I showed that earlier, the LC circuits, we could have a classical case and we could have a quantum case. At what criteria can a LC circuit change from classical to quantum? There are a few things we need to do. one is to make them very small. And how small? Basically, the effective length of the circuit needs to be smaller than the electron scattering length, because in your system is all full of electrons and they scatter, and you rely on the electrical field, your electricity to oscillate in your circuit. Then you want to make sure that it is small enough that it wouldn't be broken apart by the scattering of electrons. And you have to make the temperature low enough. And there's an equation to let you figure out how low is low. It depends on your oscillating frequency, that is your natural frequency of the circuit, and is calculated from your capacitance and inductance. And then the temperature is, K is the Boltzmann constant, and you just need to make sure that your temperature is lower than the h bar times omega. So typically we have a lot of these superconducting circuits or any quantum circuits that needs to be cooled down below liquid helium temperature. And I will show more about this in a bit. So this is what people use. The dilution refrigerator is got this very complicated structure, and it has many, many stages of electronics, but your qubit is sitting inside the very bottom. And this is what people use to cool things down to really low temperature, really low, in order to get your system into quantum regime. And I'm showing some pictures from IBM and also Microsoft, and you also have to have really precise, well-designed control system to make sure that your temperature and your rest of the circuit is not messing up with your little qubit at the very bottom. And then you immerse it in a liquid helium nitrogen dual. This is a cartoon showing how the setup looks like when you immerse the electronics into those liquid helium and nitrogen. And first, nitrogen is at a temperature of 77 K, liquid nitrogen naturally. So you can cool things down by immersing it into liquid nitrogen to 77 K, and then further down into liquid helium, which is naturally at 4.2 K. And then you can further pump your system to get to a vacuum, and there can also be phase transitions inside your system, and then you eventually can cool things down to like millikelvin temperature. And here again, to reinforce what I mentioned about temperature, is when you have any temperature in your system, the atoms and electrons are absorbing that energy, and they would vibrate at jitter. So temperature is really our enemy when it comes to quantum studies, because it's producing noise. We want to get rid of the noise. That's why we are cooling things down to so low. So all these electron scatterings and the vibration in the lattice will be reduced. And then we can look at the pure quantum behavior of your material. That's why for some of these systems, we have to cool them down to really low temperatures. Superconducting quantum computer and also the topological quantum computer, we also need to cool it down. So that was using artificial atoms to make qubits, but we could also be more creative and imaginative to not use energy levels as our zeros and ones, but we can use other types of particles or quasi particles, which are similar to natural particles, but because of the interactions between many of them, they have formed their own behaviors, and that kind of collective behavior, we call them quasi particles. So one example of using other parameters than energy level is using photons. There are photonics chips built that would guide your photons on chip, and you can manipulate its polarization. And we could encode the qubit states into different polarizations. So here are just some cartoons to show you generally. You could say when you have a vertical polarization, that's my 0 state. If I have a lateral polarization, that's my 1 state. You could use photons this way to form your 2 qubits. And Microsoft in particular is pursuing something completely different, is using a quasi-particle called Majorana zero modes. And they can be formed on a stack of different types of materials, and at their interfaces and defects, you could create them. So what we ended up using is nano wire on top of superconductors. And at the very end of the nanowires, you could create those zero modes. And the zero modes are the locations where electrons could occupy or not occupy, so leaving them empty. So you could assign those two states as your 0 and 1. This is very interesting compared to the previous examples where you rely on the individual electrons or ions to behave as your qubits. And it's very prone to your environmental entanglement. You could very easily I think this is not very quantified way of saying that, but a lot of previous ways of making a qubit can be error prone. But this topological way is to use global parameters instead of local parameters like your electron spin or where your electron is, but then to look at the global behavior of your whole system, such as conductance in your nanowire. You could have this oscillating behavior exchanging between 0 and 1 if you apply different magnetic flux. So you could assign that when your electrons are not filling up the 0 modes, that's 0. And if it is filling it up, that's 1. So I've drawn this mysterious trains here. This is trying to show that if you take this particular magnetic flux as the point you want to observe, it has a maximum value of conductance given by the 1 state. And the conductance is from the electrons flowing through the nanowire. And just imagine the case where you have a train, it needs 2 conductors to sit on each end of the train. When they are there, the train moves, so your conductance is maximum. But if you don't have the conductors, the train is stationary, so you have a 0 conductance here. So this is just to use the metaphor to show that you can have this 2 different states to be your 0 and 1, and you can exchange between them. Some papers about topological quantum computer from a while back. This is a picture showing that we are using nanowires, and you need to carefully put it onto superconductors to create such Mayer under zero modes. And you can measure its existence through global parameters like conductance. And I also have some additional cartoons to show you what is going on at a lower detail. So theoretically, you can mathematically write out the existence of an electron. And you could also mathematically write out that it could be a combination of a symmetric part or anti-symmetric part. So you could think about representing an electron using the existence of a Mayer-Önner pair. So it's all a mathematical construct, but I'm not showing any math. I'm just turning them into pictures here. And then you can have a row of electrons sitting next to each other. And each pair is paired within your electrons. But then what happens when you put them on top of a superconductor, it could make the pairing exchange. So your adjacent to symmetric or anti-symmetric part can be paired, but then leaving the ends alone, they're not paired. Now imagine you remove all of those electrons from your system, and these voids are just the locations where your pairs and electrons can sit in. Then you could have a case where you add electrons within, but then leaving those two ends empty. So that would be your zero state. And you could have a case by adding one electron, you will have those two states occupied. And it doesn't matter where each electron is, where they sit within this, as long as you have the same number of electrons within the nanowire, except the ends. If you can control that, you can create a topological qubit. So it's quite a lot of content, and topological quantum computer might be the least conceptually straightforward type. So there are some papers you can look up. I have used them, and some of the picture that I draw were basically translations of the maths that were in these papers. So if you're interested, you can look deeper and further into them. Yeah, just to wrap up, I'm showing a picture from a 2016 paper. This is a little outdated since the whole quantum computing field has advanced really rapidly in the past few years. But nevertheless, I still want to show this graph just to show it's got quite good comparisons between them. Some of the data is outdated, and like I mentioned that Honeywell and IonQ also use trapped ions. They have created more scalable solutions to trapping ions, but it's still got some limitations. I think not all of these are being used in industry at a production level. So mostly pursued ones are like the superconducting circuits that's being used by Google, IBM, ion traps, Honeywell, and IonQ. There's topological qubits. So Microsoft is doing this type, but the other kinds are still, there are a lot of research being done, but the bigger companies haven't used these much in their scalable solutions. So the biggest competitors are these ones. And also, this paper did not mention the photonics quantum computing. It's also quite new, and it could have some potential there too. So all of them have their pros and cons, and we can possibly, if people are still interested, we can dive into some of these to look at details. But in this slides, I've showed a lot of background reading materials you can use your own time to look out for. Okay, just to summarize, I shouldn't have put this slide here. I should put this slide after. I want to let people know that on Wednesday, I'm gonna do a new announcement. I'm gonna take a break from making new content, but I will still post something. And that is gonna be the certificate of taking this class. Because last time the class asked about certificate possibly by attending these classes, because we're a grassroots effort and we're just doing this for fun. We will have some reward by completing some tasks to get a certificate. And I will announce it on Wednesday. Is a personalized drawing for this class. You can put on your t-shirts or hats or emerald pin or stickers, whatever you like. But what you need to do is to complete any quantum katas, which I showed in previous classes, and this slide here, that you definitely need to go take a look at quantum katas projects, and then they have tutorials, and I also have explained a lot of concepts that you can already do these exercises with. And also, if you are keen to explore things we haven't talked about, you can try some of the katas for these topics. So any of these topics, you can pick one and do it. When you finish, take a screenshot or send a photo, post it on Twitter or LinkedIn at these accounts and hashtags, you'll get the certificate. I'll have more quizzes and have more certificates you can collect. And if you volunteer to teach at this class as an expert in any of the subtopics, we can also have a lecturer certificate. So yeah, a little overtime today, but if there's any question, I can answer now. I'm gonna stop sharing the screen. Okay, cool.
Oh, I have a couple questions.
Yeah, please.
One of them is a reasonable question and the other isn't. The first one, reasonable, is what's topological about topological computing? I understand topology to be the mathematics of things that can stretch and bend, a sort of generalization of geometry. Does that word have any bearing on the notion of topological computing?
Yeah, it is, and is the topology of the materials that you work with. They all have their electronic band structures, and that is a geometry you can imagine in the phase space. That's the, you can use topology and group theory to describe them. And in this case, it would be the topology of your superconducting circuit and your nanowire, and also the semiconductors around your whole setup. Is an interesting term you can look up for is topological semiconductor and topological insulator. And in this bigger picture, I think you can just imagine it as the same mathematics in geometry, where you don't care about local information. When two things have the same same topology, you wouldn't be able to tell them apart if you zoom in at any local information. You only can tell the difference between like a donut and a teacup if you zoom out to look at the global difference. So in this topological nanowire, when you form these major honor zero modes, and then use like a global parameter such as conductance to tell the difference between your states. That is a global picture, and you don't care about small local information like where each electron is and what their spins are. So in that way, you can also relate to topology, like how they behave. Yeah, it's not a straightforward way to explain.
No, but at least you've made some connection.
Yeah.
I have two questions, and the other one is a dumb question. One of your slides, you showed something that I see all the time when people are trying to visualize quantum computers. It's a big cylinder, glass all around it, and gold things inside. I see that kind of picture all over the place. I'm wondering what quantum computer are we looking at, and why do they all seem to be that way?
Sorry, you were cutting on and off a bit, so
Okay,
didn't
all right.
get everything.
So one of your slides, you
Yeah.
showed a picture that I see frequently when people talk about quantum computers.
Okay.
It's a big glass cylinder with gold things in it.
Okay. Yeah. The dilution refrigerator.
Yeah, my question is, what part of the quantum computer is that, and why do I see that all the time when people are visualizing these things, picturing these things in popular? There it is. Whoops.
This one.
Yeah, yep, that's it.
Yeah, the dilution refrigerator. Yeah. So all of these above are electronics and your cooling system. Only the qubits is only sitting at the very, very bottom. So all these, this skewer here is containing liquid helium and nitrogen. You're just immersing the whole thing down in here and get the tiny qubits at the bottom into the coldest area in your fridge.
Okay,
That's the setup that you need if you need to cool your system down.
and all the stuff above it is the circuitry that drives the qubits at the very bottom.
All of these above, yeah, your control system, the electronics that hooks up to your electrodes, the outside connect to your computer, and yeah, the whole thing is trying to control and cool your little qubit down here.
Awesome.
So that's another reason why we cannot have a portable. Right now, we don't have any portable quantum computers because you need a setup like this, and also like why we don't have open source quantum computer. Like the first class people ask the open source hardware for quantum computers is the complexity of this setup. So the solution to that is to make the software open source and also make the technology democratized so that people can access them through the cloud using their own local machines and then to access these complex computers through the cloud.
Okay, that's good. Thank you.
Yeah. Let's see, I saw quite a lot of messages come through. I think you showed us about, to clarify, is it how it works IRL in real life, or one way it would be created? I think Anna is helping explain that, but I'm not quite sure what Isho is referring to.
I think that was about the ion trapping, whether it's how it's practically made, or like whether it's practical in real life.
Yeah, it's actually usable now, the ion traps. There are on-chip solutions where you can trap your ions on your chip and then you manipulate each ions electrical field around them, or use lasers to point at them to manipulate them. So startups, IonQ is a startup. Honeywell is not a startup, but both of them are using ion trap methods. They all have their pros and cons exactly. So that's for hardware. This is a really evolving field, and I mentioned that no one is an expert in all of these because every day there's progress made in all of these hardware setups. So it's still very early to say which type is going to be used first and last. So we should read, learn, and see what happens. Jimmy asks, with an oscillating state, can the distribution of ones and zeros be controlled to be either evenly split or half weighted? Yes, you can control how much. Basically, zero and ones are in superposition, so you can control the weight of each. Helium-3 costs a lot of money. Mohit, we need vacuum to keep the temperature low. Yeah, we need we need vacuum to insulate your setup. One of the requirements, yeah, Anna, thanks for answering those questions. One of the requirements for a qubit to be useful is to be able to prepare it in an initial state. So technically, you should be able to create any kind of population distribution of ones and zeros. Yep. How it is done practically with oscillators? Okay. You can apply. So the oscillating circuits are on chip, and you can build transmission lines to apply electromagnetic field. So all of these, if you look at all of these systems, they're just using either electromagnetic field or light, and they're the same thing, but at different frequencies. In those oscillating fields, they are at microwave frequency. You can apply that electromagnetic microwave through your transmission line on chip and be able to tune where your superposition sits at. For MV Center, Anna, did you work on MV Center in the labs? I don't remember your research.
Yeah, I did a bit. I was all over the place with my research, but I did work with MV Center.
Yeah, cool. Thank you. So you change the populations of ones and zeros by shining green light, yeah, of a particular intensity and duration, and then you apply pulses at gigahertz frequency to split the spins, perform entanglement. How do you do readout? How do you?
You look at the fluorescence. So the fluorescence of the 0 and the 1 state is different. So you look at the average fluorescence over as you do the manipulation.
And at what frequency are these fluorescence? Microwave?
No, the fluorescence is in the red. So you pump.
Oh, it's optical.
Yeah, it's optical. So you pump with green light and you read out with red, and then you deliver microwave to flip the spin, and that's at around 3 gigahertz. It's 2.87 gigahertz, but it depends if you also have an external magnetic field applied.
Right. Well, thank you. Mohit says, I believe you need vacuum to remove gaseous molecules. Sure, that's you should do that too. That would otherwise freeze in your system and cause catastrophic. Yeah, sure. Yes, you don't want contamination. Yeah, quite a lot of discussion about the vacuum. Thanks, Benjamin, for liking the content. But I do like to see people actively working on programming. So I do want to reward you with whatever. Well, that is the nesting of Nathan says nesting of different refrigerators at progressively lower temperatures. Yeah. Yeah, so hardware is very difficult, but we can do a lot as individuals to work on the software and utilize all these large-scale hardware. So I think it's very exciting that we have these progress made together, both in terms of software and hardware, and be able to learn as the field develops and be able to use what we are learning immediately into coding and programming. So one of the challenges besides building the quantum hardware is come up with interesting algorithms that are useful. There are historically a few algorithms developed, and we will go into each of them and try to program them and just practice our understanding of how the quantum algorithms work. And the field needs a lot more specific solutions to problems that could use quantum methods. So once you practice more and learn more about quantum computing, there's a huge number of opportunities for you to contribute and be a quantum developer to come up with new algorithms that no one have thought of before to solve certain problems. So the opportunities and challenges are unlimited. And that's what's making it very exciting right now. How are quantum logic gates implemented on hardware? So yeah, so for different types of hardware, you would do it differently. And as I mentioned earlier, we build those setup, we define our states, and then we use microwaves or optical light to manipulate your system. Is using the your system's interaction with electromagnetic field. So, for example, if you use the spin up of your iron as your 1, and you could shine some laser lights to rotate it, to flip its spin, to point down, and that would be your 0. And based on how you place them, that's implementing your gate, because your gate is, say, an X gate is flipping. So you would apply certain type of laser light to flip it, and that's effectively applying an X gate onto your iron. Oh, Anna is also given the trapped electron in this case, trap iron in the laser light field. Yeah, exactly. So just remember that those are just matrices that you can physically translate to what your qubits are. And I think I missed a slide. I didn't show this picture in the slide. It's just something I found very cool in physics, is the relations and similarities between different systems. Let me find that picture. Okay. Share my screen now. So here I'm showing you the equations, Hamiltonians of different oscillating systems. Like I mentioned the swing And it's just a weight on the string that is oscillating, or you can have a weight on the spring, or you can have the LC circuit, which is an oscillating circuit, and you can replace the inductor with the Josephson junction. And also in your nuclear, your atom, the nuclear and electron could be modeled like a similar oscillating system. And if you look at their Hamiltonians, they have very, very similar behaviors. And that's what physics is about, is modeling things, and you realize all these microscopic or macroscopic scaled systems are actually behaving in the same way. So I just wanted to show this. It's very cool. And just now when I mentioned the LC circuits, what the Josephson junction does is to change the profile of a harmonic oscillator into this weighted profile. That we can actually do that same thing with a weight, a swing, where the gravitational acceleration is effectively changing the profile of your oscillating harmonic oscillator. So if you move from Earth to Mars, your G, the gravitational acceleration, will be different, and that could effectively change the profile, the energy profile of your weight on a string to a similar effect as the Josephson junction to an LC circuit. I don't know if that makes sense. Okay, we are way over time today. I think we're gonna stop here. Is there any more questions? Yeah, I'm glad that people found that beautiful too. Am I going to add the slides to the current? Yeah, of course. I will add those on Hackaday project. Classical gates are so much easier. I don't know about that. You just need to get used to it. How many controlled quantum gates are used in typical quantum computer? Oh, that's depends on your algorithm. We'll show some algorithm later, like Shor's algorithm for factorization, Gruber's algorithm for search. They all use a lot of gates. Yeah, okay. Thank you. That's it. And we may, remember the certificates, and I may move to Twitch next week. We will see. Thanks, everyone.
Thanks, Kitty.
Bye.
Thank you.
Thank you.